Okay. Huh? Oh, oh yeah, it's going really slowly. I was thinking I should probably take attendance. Hmm. Well, I'm still concerned about registration issues, but unfortunately, no one in here is having registration issues. Because I still have people missing from my roster and some of your classmates that should be here, but there's been some financial aid snafu. So oh yeah, deadline to register is Monday too. So if your friends are not registered, tell them to get that in ASAP. Yeah. Right, so I'm just pulling up attendance. So yeah, we left off on this problem. So while I quickly take attendance, since I think I know everybody, you can work on this. Okay. Are you getting registration issues fixed? Are you going to be registered? Did they say? Okay. Yeah, they're making a mess of that, and I'm pretty upset because like at this point, 8% of my students have been affected, which is like I don't even know how that's statistically possible. Then I'm even more angry because like the majority of those are in the last of a series, so that's obviously affecting people's graduations and applications. So yeah. Anyways, I was gonna say if it wasn't solved, start a riot with the other students, but. All right, so we left off on here. Did we have a chance to look at it, think about it? Yeah, I mean you could, or I mean I was thinking even easier, just plug it into Henderson and Hasselbalch. Yeah, so probably so we can use our HH equation. So pH equals pKa plus log of our base over acid. And then, so what's our starting point then? So we want to get a pH of 4.25. So what's a good acid to even start with? Somebody said, did you say it back there? I was like, yeah, formic. So you can just take the difference and, maybe you have to use a calculator for this one. But yeah, just seeing which one's closest. And so I think we can tell that chlorus and hypochlorous are pretty far. And then, so let's take 4.25. So minus, so the other option would have been nitrous, but that's obviously lower. Sorry, I'm not thinking this morning. So yeah, so formic is much closer. So good. So let's just say start there. So start with formic acid. So we have a desired pH of 4.25 equals, so our pKa, we can plug this in. And then find our ratio, right, of our conjugate base to our acid. So now we can solve from here. So subtract. So then 0.51 is equal to our log ratio of base over acid. And then of course log base 10, so we can take 10 to the power of these things, so that gets rid of the log. And so now let me plug in 10 to the power of 0.5, or 0.51. So 3.23. And so that just means that that's our ratio, right? And so now we could just come up with whatever ratio. Did it say an original? So it doesn't tell us, right, how much we're making, but just as long as we're in this 3 ratio, right? So that'd be a 3.23 to 1 ratio, so molar solution. And so that would be of molar. And so what's our conjugate base then of formic acid? So formate, so then we have to pick whatever salt. I'll just pick sodium for good measure. So sodium formate. And again, just going with a 3.23 molar solution to a 1 molar formic acid there. Does that make sense for that one? Oh, because it was the one that was closest, right, to 4. Yeah, I mean, you're just trying to figure out, like, okay, here's my desired pH. And of course, this is also, like, assuming that there's no other factors, right? Like, we didn't say anything about, like, what system this is going in and if there's any other counter ions or reactions. But, yeah, if we're just, like, trying to hit a desired pH, you know, you just have to go through your acid. So if you had another one, like, I would have to go back to our full list of acids. And we could try to see if there might have been any other better choices, right? Where's our acid list from last quarter? There it is. So I was trying to find, so looking at this other table, again, not all inclusive, right? So if we had had some benzoic acid, you know, that would have been good, or acetic acid is right there already, right? Pretty close. So it just depends what acid we were starting with. So yeah, if you were like sitting in a lab trying to figure out and you could pick anything, then yeah, you could pull up this table, well, which one is closest to my desired pH, and then go from there. Or, like I said, if you're trying to create a specific buffer, like let's say, oh, well, I have to use phosphoric acid or something, then, you know, obviously you have to start from there and tweak it. So it just kind of depends. Oh, not CHEM 104. All right, good. All right, so now we're going to go back kind of through titration, and this will really help us with the first lab. So I know we've kind of done it, but we're going to hit a few points and probably go back to chapter 20 homework for a little bit as well and kind of look at some of the diprotic, triprotic acid stuff. And so, okay, kind of basics of titration, and then this corresponds to your lab that you're doing today. So we're doing, and if you already did it, so we're doing 3 types of titrations, right? So you're doing a strong acid, strong base, and so we'll look at that. And then we're doing, right, weak acid, strong base, and then no one gets to it, but in theory, or you can at least graph, right, the data for the triprotic acid. Okay, so now we have to kind of define these points. So I think we kind of know some of these. So of course we have an unknown concentration. So that is what we're titrating, right, with our acid, or, well, we started with a known in this case, and again watched our titration curve. We have our burettes, and again, we've talked about this point, so let's go through it again. So the equivalence point is defined again where your moles of acid equal your moles of base. And so that's right for your kind of 1-to-1, like HCl to NaOH titration, right? So that's your main equivalence point. So monoprotic acid. And then of course we have different indicators, and again we choose phenolphthalein because that is where it mainly corresponds to our endpoint going from acidic to basic. Of course, this gets into if you're truly doing a triprotic acid, then you might want to get some sort of universal indicator or other indicator that is more precise for what you're going for. And then again, the endpoint is just where it transitions. Like we've looked at, some indicators, right, have multiple transition points. And again, that's what dictates, like whatever endpoint you're interested in is what indicator you select. So I think we know that. All right, so let's get to more of the math and kind of break this stuff down. And so, okay, sorry. I'm just trying to, I want to make this really clear because people get confused. So we'll first start, we'll do an example with this, but let's look at like where we're going. And I was trying to explain this in lab to some people. And so of course we're doing this plot, but the whole point of the plot, and I'll just break this down, is we basically have 2 different scenarios, and then there's 3 different points in how we mathematically treat them. So like I said, we have a strong acid plus strong base, and that's the first one we do, and that's pretty easy. And so it's going to be here, right? So strong acid, strong base. And so think about what that means again with the definition of the neutral salt, right? So that means that when we add them together, and let's just, again, I just want to be really clear because people get always confused every year, and I hear the tutoring center usually also gets confused every year. So I wouldn't expect them to be a good resource. Not trying to be mean, it's just that it is what it is. Okay, so we make this salt, and so this salt is neutral. So that matters because, well, when we reach our equivalence point, well, this is the salt that is generated, right? So it does not have an effect on the pH. So that means at the equivalence point, right, when we have a strong acid, strong base, the pH is 7. So now thinking back to your lab and how, because you're going to have to set up a bunch of Excel calculations probably. So in your strong acid, strong base scenario, you're going to have your kind of prior to equivalence point. And essentially you just do the reaction. And so before the equivalence point, you should have excess HCl, right? And so you're trying to figure out how much is left, which corresponds, right, to your molarity. Of course, I'll just say you'll have to do a volume adjustment. That'll become apparent when you're in lab. But basically, okay, right, the big picture idea, do the reaction. It's a straight neutralization. You just have to figure out how many H plus ions are left over, or HCl molarity, right? That corresponds directly to your hydronium molarity. Again, strong acid. Okay, so is that kind of simple enough? So that should just be like simple stoichiometry for you guys. And then again, 1-to-1 ratio. And I'll just kind of reiterate this. So now at equivalence point, we can just assume that the pH is 7, right? And I don't even necessarily need to see calculations for this. You can just state strong acid plus strong base, you know, at equivalence point, 1-to-1 molar ratio, we know our pH is 7. Because again, it goes back to our salt. And then, okay, so then we have after the equivalence point, Now, if you're doing this on Excel, right, you're going to have to set up kind of a new calculation, because now what you're trying to find, so you'll still do the reaction, right? But except this time you're going to have excess hydroxide. So you're going to be subtracting your HCl, right? Figuring how much is left over. And again, it's a strong base, so that concentration of hydroxide, again, right, convert to molarity. I'll just say volume adjustment again. But that corresponds to your hydronium concentration directly, right? All fully disassociated. And then, of course, you can get POH to pH. So that's, again, your strong acid, strong base treatment. And then, like I said, we're going to hopefully go through a lot of this math today, maybe even steal recitation time to go through this math. But then, alternatively, the other scenario that we'll look at is then our weak acid, strong base. And so the caveat with the weak acid, strong base is, so let's look at this. So we still have, so let's go before our equivalence point. And so before our equivalence point, it's generally okay to use Henderson-Hasselbalch. And then we'll say, like, of course, rice is always appropriate. But again, in the case, just thinking of your lab, your titration, so what you're going to be doing, right, Henderson-Hasselbalch, you do have to keep in mind, I'll just say Ka, right, pKa. So keep that in mind. Again, right, do reaction. And then get our ratio, right, of base to acid. So that's what that's saying, right? So you have your reaction. And so that's the key point with this weak acid, strong base, is you start with your acid, but then after the reaction, you're forming that conjugate base, right? So then your reaction, you're calculating this ratio at every point. And then, like I mentioned, volume should cancel out. And now we'll talk about at the equivalence point, but then we'll have to go through an example to make this clearer. And so now let's look at the equivalence point. So yes, right, our moles are still formally 1-to-1, right, acid to base. But let's go back at our notes. Well, we'll look at our notes. Let me write this out. Sorry, I'm getting excited. Man, I can't remember the formula for acetic acid to save my life for some reason. All right, so then we form, right, acetate and water here. And so what is the problem with acetate? What's different compared to our product of NaCl? Yeah, so it rebounds with the hydrogen, meaning that this is a basic salt, right? And so this is where we can't just assume that it's pH 7, correct? And so this is the tricky part of the titration. And it does tell us this in our notes, so we'll look at this in our notes for a second. And so it reminds us here the equivalent point of an acidic salt is going to be less than 7. Well, actually, that's not how I like. I think your notes, sorry, your titration notes said it better. That's true, but that's not what I was thinking. So right in your weak acid on your notes, it says that your equivalence point for your weak acid is going to be greater than 7. And that's actually, I wanted to write that on the notes. So let's put that. So your weak acid should have equivalence point greater than 7. And so this kind of explained the other side of it, right? But then you had to recognize that acetate was a basic salt. So that's why I think it's much easier to express it this way. And then same way. So that means a weak base, then we'll have an equivalence point less than 7 for the same reasons, right? So then the weak base, it's going to react, make the conjugate acid salt of ammonium, so then that's going to drop the pH there. But like I said, we'll go through an example once we kind of lay out our, we'll call it 6 basic scenarios, right? And so that means that we have to then, right, use our KB, PKB of our salt, which like I said, we'll go through this so you can exactly see how we treat that. And again, right, given our molarity of the salt, figure out how much OH. And again, let's write this out so we're clear. Okay, yes, just like Ellen stated, it's going to reform, right? So now we're going to make our acetic acid, and then in the process, make hydroxide, making it a base, or slightly basic. Yeah, so then you can use the Ka to find the PKB. But like I said, we'll go through an example all together because, yeah, it can be tricky. And then once you get past the equivalence point, I feel like you're kind of home free though, right? So now past equivalence, it just turns into an excess hydroxide case again, right? So now at this point, you've completely neutralized our acetic acid. Any sort of effects of the acetate being basic, right, are going to be pretty irrelevant compared to your excess hydroxide at this point. So then at this point, you go back to figuring out, right, again, you do the reaction, figure out how much is left, and then of course, right, adjust for molarity, and then back to POH, pH scenario. Is that kind of at least like makes sense with the overview? It's like, okay, this is where we're going, and now we'll practice these scenarios. But when you're doing it, and this is what I find that like most students struggle with, is like they're looking at the scenario and then they like forget how to mathematically treat it, right? So then you have to look at your word problem and say, well, where are we, right? Is this first a strong acid, strong base? Are we before the equivalence point, at it, or after? And then same thing, is it a weak acid, strong base? Or, you know, we could technically see a weak base, strong acid. I'll put that in parentheses, right? Weak base, strong acid. So I would also not give you a weak acid, weak base titration, right? That would be too terrible trying to figure out what the heck is going on. So that's not what we're going to be doing in our class. All right, just kind of make sure we're okay with our general overview. So let's start with this real quick. And so now we're titrating 50 milliliters of a 0.2 molar sodium hydroxide with 0.2 molars of nitric acid. So calculate our pH after 30 and then at the equivalence point. I had the mute button on. So new molarity, so moles over liter. So 0.004 divided by 0.08, new volume. So that's our new molarity. So now we can, this case, right, they almost kind of tricked us because usually we go the other way, but this time, right, we're solving for POH first. So now let's get our POH. So negative log of this. So POH and then 14 minus that to give us our pH. And let me write that down. So 1.30 roughly for POH. And then pH is 12.70. Questions on that one? So that one's pretty straightforward. And then B, right? So what do we know about B? So the moles are the same, and then if it's neutral, what does that make our pH? 7. So perfect. So, oh, and this was nitric. So again, pH 7. I'll just keep writing, again, neutral salt. So we remind ourselves that, yes, this is only for the neutral salt scenario. And again, this is totally appropriate to just write on the exam like this at this point. Like this is by definition now. All right, good. Let's keep moving on. And so now we'll look at our weak acid strong base titration. And so we'll prove this in our examples, but we have, again, our other key point. I mentioned this in lab, but we'll mention it again. So our half neutralization point is a pKa. Ideally, you would, if you were titrating the acetic acid, you would kind of see this like inflection point, but like as indicated here. But most people didn't make it to the acetic acid, but you could still graph the dummy data and hopefully see that. And then again, it's reminding us that we can use, right, our reaction stoichiometry and then Henderson-Hasselbalch after doing that reaction, right? Because again, you're comparing how much conjugate base did I make compared to how much acid is remaining. And again, we'll work this out in just a second. All right, so let's see if we can try this. So A should be fairly straightforward. So just take a second for that. So volume required to reach equivalence point. So what's our volume to reach equivalence point? What did you say, 20? Yep, so 20. So you could, of course, right, multiply this out. and see how many moles that is. So I guess I'll write that out. So 0.04 times 0.1, so 0.004 moles of our nitrous acid. And then, so we have 0.004, so we need 0.004 moles of our base. So we have our 0.2 molar solution, so moles over liters. Just setting it up as proportion. And we should get 20 once we punch this in. So 0.02 liters or 20, so excellent. All right, so now let's see if you can do it on your own for a second. Right, so set up your rice table, calculate your moles. So now what's our pH after adding our 5 mils of KOH? And I'll just put HH here, right? So use Henderson-Hasselbalch. So I'll start kind of just sketching it out. Just starting with our reaction. And of course, right, our potassium nitrite is a basic salt. So I'll just kind of put this, again, reminding us that this will react with water to reform, right, our nitrous acid. And then also, of course, form our base, hydroxide. So again, this is telling us like why we need to use our Henderson-Hasselbalch equation. So we have to account for this. All right, so then hopefully y'all calculated moles of everything. So let's see. So we still have 0.004 moles here of our nitrous. And then, so let's see how many moles we had of this. Oh, sorry. So 0.2 times 0.005, so 1 millimole. And then now we do our reaction or change. So, okay, do the reaction. So minus 0.001 minus 0.001. So that is all going to be consumed. So it kind of helps maybe to write some of these equilibrium values as well. And then, of course, we're going to make so plus 0.001 moles of our conjugate base. All right. And so now we can calculate our new volume, although for this case, right, it shouldn't matter because new volume will cancel out. And so now we can plug this into our Henderson-Hasselbalch. They didn't give us our pKa here. Let's go look it up on our old notes. Because if you do, right, because molarity is moles over liters. So let me write it out. Well, first let me get our, so pKa looks like it's 3.34. And then, yeah, in this case, right, so our Henderson-Hasselbalch is pH is equal to pKa plus log of the molarity, right, which is moles over liters, moles over liters. So that's why I was saying, right, liters cancels out in this case, so it doesn't matter. So we don't have to worry about the volume adjustment. Even though I still say, like, just keep it in the back of your mind, right? Because some of these problems, it matters. Again, like with our titration, you do have to keep track of the volume. This one, again, it cancels out, luckily for us. And so now we're left with pH equals 3.34 plus my log of my base, so 0.001 over 0.003. And so now let me plug this into the calculator. And I guess I could just put 1/3, right? It's all about the ratio. And did I do that right? Is that what y'all get? It seems funny. Maybe it's right. Sorry, I was just double checking. All right, that should be correct. So we should get 2.86. Is that what we get? So pH 2.86. And then, so now let's take a look at C, pH at 1/2 the equivalence point. And then I'll probably add in there part D of at equivalence point. Because that's in your homework, but like I said, I want to go through that together with the treatment of the KB and all that. So try to do C. And again, it might become obvious why the formula is the formula. Yep. Or you could say, right, where moles equals half. That's like another shortcut. And then you'll quickly see why the pH equals the pKa. Oh, just where like you're halfway to the equivalence point. So if you're titrating your acid and adding base, then you just want to say that your moles of your base, right, is half of the moles of acid. Or like she said, right, since we calculated the equivalence point to be 20, halfway there would be 10. So either way to think about it in moles or volume. And then again, do recall by definition, it's going to be the pKa. We're just kind of proving this currently. Oops, what am I doing? And so what do you notice about your amounts of your base and your acid at the half equivalence point? What do we notice here? Going back to our Henderson-Hasselbalch. So why does the formula tease out too? You could say it. Huh? Well, what are the numbers? Yeah, they're equal. Don't be shy, guys. I'm ready to like start picking on all of you. But yeah, so they're equal, right? And it's okay if they're equal. You divide them, they're 1. And well, what's the log of 1? So 0. And right, you can always plug that back into the calculator. We forget. So log 1, 0. So now we're back at the pH equals the pKa at our half equivalence point. So then what was that? 3.34? I forgot. All right, excellent. So let's do one more to this. Like I said, we'll probably go a little over time. And I mean, of course, you're always welcome to do what you want with your time. I do have the welcome quiz, but we'll save that for the end since, I mean, I feel like I know you guys, and this is probably more important. So let's try at the equivalence point for this. And so again, right, the issue is that this is, of course, non-innocent, so it's a basic salt. So I'll kind of let you try it for a second, see if you can figure out what to do. I mentioned, right, we're going to have to figure out our pKb. And well, we have our pKa at least. So I'll let you start that. Oops. So how are we doing with this one? I kind of try to sketch out our initial conditions. So the key point being we have to figure out, well, how many moles of basic salt did we make? And then we do have to calculate our new volume now. And so now, what's our new volume? So good thing we had this calculated. So 40 plus 20, so it looks like 60, correct, is our new volume. So 60 milliliters. And then from here, we have new molarity of our base, so potassium nitrate salt. So is this clear so far? And so now from here, it is basically just our equilibrium expression, but in this case, right, it's our Kb. So let's write out again what is our relevant reaction. So that's potassium nitrate is going to react with water because again it's neutral to give us our acid back again and hydroxide. So again, trying to figure out the pOH off of our hydroxide concentration. So we have to do our equilibrium Rice table expression. So right initially, so now we can plug in our molarity that we found. So new adjusted molarity. And then, right, nothing's disassociated yet, so it's going to be moving in the forward direction. So change, right, minus x plus x plus x. Again, we're trying to figure out how much hydroxide is formed. Then equilibrium. Okay, so then we still have to calculate the Kb, right? So this is kind of a quick aside somewhere. So we said that the Ka was 3.34. So that means the Kb is 14 minus that. Or, yeah, sorry, you're right. So pKb. So then the pKb is 10.66, which means our Kb is 10 to the negative power of our Kb. And you could also, right, look this up online. I would imagine there'd be small discrepancies. So I'll look it up for fun if I can find it. So nitrite Kb, let's just see what a quick search says. It's actually pretty close to what we calculated. I mean, yeah, it is what we calculated. So we have about I'll use our number, so 2.19 times 10 to the negative 11, which is roughly what Google pulled up here. They said 2.17 to 2.25. So again, you're going to see minor discrepancies with this. Okay, so now that we have our Kb, we can go back to equilibrium expression. So now plug this in. So now we have our KB is equal to, well, let me just write this out. So OH times A minus, or sorry, times HA, excuse me, over A minus, which is equal to, so X over 0.0667 minus X. So that looked good. And then we could probably make an approximation, right? That'll help us a little bit at least. So negative 11 is pretty tiny. So we could probably simplify this to x squared over 0.0667 is equal to this number. And so now let me just finish plugging this in. And so this is, again, our hydroxide concentration. So 1.21 times 10 to the negative 6. So this is equal to, or excuse me, I keep jumping the gun. Hydroxide. So then solving for POH. So 5.91 is our POH, which makes sense because we said our pH should be a little basic. So let's see that. So yes, right, about 8.08. For our pH then, again, at the equivalence point for that salt. Questions on that one? So again, this will be important. Help you with the lab too. And then I did want to go over back to the chapter 20 homework because we didn't really talk about the polyprotic acids and the dissociation constants. Oh, yeah, yeah. If you guys want to, we could take a break. I was just like trying to keep going. But yeah, we could take a break. I'll hand out the quiz in case people want to like sneak out or anything. It's just a welcome quiz. But yeah, and of course you can catch this later. Oh, I don't have the correct welcome quiz. Okay, let me go print out a new welcome quiz. But yeah, we'll take a quick break then. But I did want to keep just going over the acid-base stuff since we don't have a quiz. All right, break. All right. So like I said, we're just trying to go over some of the chapter 20 stuff that we didn't really touch on. So let's look at, I'm just looking at the homework, like back. So this is chapter 20 homework. Yeah, I was just going to start with number 1, really, because I just wanted to go over, maybe not. Yeah, number 1, I think is okay. Because, yeah, we just want to go over kind of the answer key and what it's saying. So it says, so calculate the pH and equilibrium concentrations. And it wants, so our system, so carbonic acid, bicarbonate, and carbonate for a 0.0750 molar solution of carbonic acid. All right, so then the way to treat these is first you have to know whether like the first dissociation, yeah, is strong. Oh, sorry. Thanks. So yeah, the first thing to evaluate is whether, right, your first dissociation is strong or weak. And so this one, right, it's a weak. And so that's probably something that we just have to look up. I know it says that the ionization constants are found in the table. And again, I would expect some discrepancies. So our pKa1, so again, just showing us that we have equilibrium, is 6.35. Our second dissociation is 10.33 for our pKa. And that make again 2 pKa is corresponding to our 2 dissociations, right, for our diprotic acid. And then just looking at the homework and kind of comparing and talking, just so you kind of have this in the back of your mind for chapter 20. And if I need to post like chapter 20 in the third Blackboard again, let me know. I can do that. I forgot you guys don't have like Blackboard 20 access anymore, and it might be helpful to review that. But yeah, so like looking at 2 or like comparing, so that one involves sulfuric acid. So that one, right, the first dissociation is strong, so you just convert that completely. But otherwise, right, you just get the pKa of each one. All right, so then we start off with our rice table. And basically we do, again, we just start with our first dissociation and setting up the math for that. So then that means that we start with our carbonic acid, and then it's going to dissociate into H+, and then our bicarbonate. And so that just starts off with, so we have 0.075 molar. Okay. And then let's think about, so that's our initial. And then our change, okay, so it's going to be going in the forward direction. So then that's going to be minus x, okay, plus x here. All right, so that's our first step. And then again, we're trying to figure out our pH. But then kind of the tricky part is, well, we have to calculate, right, from our second dissociation step. So let's start to outline that out. So we have, right, so the problem is, of course, this carbonic acid here, or bicarbonate, excuse me. So bicarbonate, of course, goes on to dissociate as well, right, to H plus carbonate. And so that means when we're trying to calculate our equilibrium, well, this is going to be minus y, right? And then we're going to have, so just starting with this, well, whatever concentration is going to have to be from here. So initially x minus y. And again, y is how much is, this is disassociating now. And then our total H plus, right? So we can't forget this one. So both of these count. So x plus y. And then so carbonate is only y, so plus y here. Okay, I think that's looking pretty good now. Oh, and then let's include x plus y over here, right? So we can't forget about that over here. All right, so I think we're ready to start solving. So once we've kind of accounted for where all the species are going. But again, we're going to kind of like resimplify because you can see there's a pretty large magnitude between these. And so now let's turn our pKa into our Ka. So 10 to the power of this, negative power of this number. So we can start setting up our expression. So that's 4.47 all around it times 10 to the negative 7 is equal to, so now x plus y, right, times x minus y, all over 0.075 minus x. And so, of course, you can start to see, like, if you were maybe doing some research or doing some more, like, advanced modeling or small calculations, right, where you can't make these assumptions, you'd probably have to plug all these systems of equations into, like, a computer would be helpful. Oh, thank you. Otherwise, right, again, we're comparing our difference in the order of magnitude, so pretty big. So, right, 10 minus 6 is roughly 4, so I'm expecting like, 10 to the 4 difference roughly, which is appropriate to then make our assumptions. So, right, now we can do our 5% assumption. And then we get, so obviously the 5% assumption makes it a lot easier, so that y goes away, x goes away, so then we're left with x squared over 0.075, because again, we're saying this change in y is irrelevant, this change in x is pretty small, and now we can solve. And then let's go ahead and double check our assumption for this. So what was our original concentration? So 0.075. I think we should be safe, just judging. So yep, 1, 2, so 0.2%. So yes, we are safe. And so yes, that is our correct assumption. So x equals 1.83 times 10 to the negative 4th here. All right, so now we should be ready to do our next one. And again, kind of doing the same sort of assumptions. So we had left off over here. And let's see. Do we need a value? So let's calculate. So we need our pKa, or excuse me, our Ka. Keep saying those backwards. So our second disassociation was so that means our pKa, oh, sorry, I did it again. Ka is equal to 10 to the power of negative pKa. So that gives us a Ka. Oops, I think I plugged that in wrong. Sorry, 10.33. one more time. All right, so that looks better. So then we get our 4.68 times 10 to the negative 11 is equal to, so now we have x plus y times y over x minus y. And then again, right, really small, so we can make our 5% assumption again. To get us to, so 4.68 times 10 to the negative 11. So times x times y over x. X cancels to leave you with y, which, I mean, it's basically to say, right, it's pretty dependent upon your disassociation constant anyways. So y equals 4.68 times 10 to the negative 11 there. And then, so then we can figure out, right, our total concentrations of everything. So going back to what it asked us for. So then starting with this, so kind of going back to our reference here. Well, it's minus x, so now we have to replug in that value of x. So 0.075 minus 1.83 times 10 to the negative 4th. So pretty small change. So 0.078, oh, so 0.0748 molarity. And then, let's see, did it ask us? It didn't ask us for H plus, did it? So we could calculate it. I think that was in the answer key. But right, so H plus is then X plus Y. Well, I don't know how significant Y is, right? That disassociation is pretty small. So 1.83 times 10 to the negative 4th plus our Y value. So pretty much gives us the same answer. So again, that second disassociation didn't do too much, but still good to keep track of. Oh, sorry. So 1.83 times 10 to the negative 4th. So let's do our hydrogen carbonate. So again, that one is technically x minus y, but I think y is going to be so small. I'll just punch that out, right? And again, if your numbers were different, right, it may not be insignificant, but so it's probably going to be insignificant. So yeah, it still rounds, right? So 1.8299 or 1.8. And then our carbonate. So looking at our carbonate, so that was just the value of y, so we can just plug that one in of about, what did we say, 4.68 times 10 to the negative 11 there. Oh, and then pH, so of course we can calculate that. So negative log of 1.83, which was again mainly dependent upon our first disassociation anyways. It's also just showing for the most part, right, your first disassociation is going to dominate. So 3.74 for our pH there. Thank you. Questions about that? So at least like take it in, right? See, the whole point is just to kind of keep track of who's going where, who's reacting, what's going on. And these are good concepts just to keep in mind. I would have to look at my tests, honestly, to see how hard I'm going to test you over this, or I don't remember if I do or don't at this point. But we still want to keep this in mind for like common ion effect. It's going to come back with solubility, again, just like keeping track of the ions and kind of where they're going. But again, the point was also to see once you have this large difference in disassociation, right? It's mainly the first one, anyways, that dominates the behavior. All right, I've probably taken enough of your recitation time, but that being said, right, again, it's just a welcome quiz this week. So if there are still lingering questions from last quarter, that now would be a good time to go over them. I don't know if anyone had any like big questions that we could work out for everybody. Otherwise, I'll probably just like stop the stream and let people ask anything individual. And I think I covered the lab. So like I said, the lab this week is basically just deciding between what scenarios you're on. So kind of going back to my, I'll call it my cheat sheet here, right? But it's basically, are we again strong acid, strong base? Are we doing weak plus a strong? And then going from there, right? And then you have before equivalence point, at equivalence point, after equivalence point. So you just have to pick which of the essentially 6 scenarios you're at and then treat it mathematically. All right, I'll probably stop my formal lecture, but like I said, use this time wisely, ask questions. We'll be doing the same stuff in lab, and it'll be good practice. I'm just watching the stream in case there's any last minute questions or problems people want me to go over. Like I said, either from chapter 20. Otherwise, thank you. Appreciate the quizzes. Thank you. Let's see. Then, oh, here it is.